Welcome back to The Deep Dive. If you've been online at all recently, you've probably seen it, one of those slick videos. A humanoid robot doing something surprisingly agile.
Yeah, balancing, walking, maybe even that kung fu move.
Exactly. We are talking about Optimus, Tesla's big push into humanoid robotics.
And those clips, they really go viral, don't they? So our mission today, I think, is pretty critical. We need to kind of decode the science, separate it from the usual hype around Musk projects. The big question really is this robot genuinely on track for, production and real autonomy? Or is it still fundamentally a very, very expensive R&D project?
That distinction matters hugely, doesn't it? Because they're not pitching this as just some lab experiment. The sources, like Tesla's own AI page, state the goal very clearly. A general purpose, bipedal, autonomous humanoid, and the specific aim. Performing tasks that are unsafe, repetitive, or, frankly, just boring for humans.
That's the core of it. It's not a side gig. It ties directly into their whole AI roadmap, their compute strategy, if Optimus actually works at scale.
It changes things.
It fundamentally shifts labor economics, manufacturing, logistics, everything.
Okay, let's unpack the latest evidence then. That viral clip you mentioned, the one Musk posted, picked up everywhere from the Times of India to Cinco Dias.
The Kung Fu demo.
Yes. What was the significant takeaway there, beyond just looking cool?
Well, visually, it was impressive. The motion seemed quite fluid, quick stance changes. Definitely a step up from earlier demos we've seen.
Yeah.
But the real engineering feat wasn't the kick itself.
It was the recovery.
Exactly, the recovery.
You mean that bit where it gets nudged or pushed and manages to stay upright? How big a deal is that reactive stability?
Well, it's massive because it's showing robust closed-loop feedback actually working.
Okay, closed-loop feedback. For listeners, maybe explain how that's different from a robot just, running a pre-programmed routine.
Sure. Think about walking on a perfectly flat, dry sidewalk versus trying to walk across, say, a patch of black ice. A robot just following a script that's open loop. It executes step A, then step B. If it hits the ice, whoops, it's down. Because the ice wasn't in the script.
It can't adapt.
Precisely. Closed loop means the robot senses that slip the unexpected change to its balance, its center of mass, and it instantly calculates and executes a corrective action. Maybe a quick foot shuffle, a lean.
The step C.
Step C, exactly.
Okay.
A step that wasn't explicitly programmed for that specific slip. It's reacting to real physics in milliseconds. So, using something like martial arts for training.
It's a stress test.
It's a brutal stress test. High-speed changes in center of mass. It suggests real progress in locomotion control, something much more robust than just basic walking on a flat surface.
And that level of control, that sophistication, it didn't just appear. There's reporting, I think, from eWeek indicating a really fundamental shift in how Tesla is training Optimus.
Yes, a major strategic shift. They seem to be moving away quite drastically from the traditional methods. Things like motion capture suits or even direct teleoperation where a human is puppeteering the robot. They're shifting towards something, riskier, but potentially much more scalable. Vision-only learning.
Vision-only, intuitively that sounds harder. Why not use mocap if it gives you precise movements?
Because that precision often doesn't generalize. You can mocap a robot to do a task perfectly in one specific setup. But change the lighting, change the tool slightly, move the table, and it can fail completely. It learned the exact movements, not the underlying goal or how to adapt visually.
So vision only is about the robot learning by watching, observing the world or videos of humans and figuring out how to map what it sees to its own movements.
That's the ambition, yes. It's like the difference between someone telling you exactly how to position your arm to throw a ball versus you watching thousands of videos of pitchers and figuring out the kinetics yourself.
Right.
They pull this off. I mean, the potential for rapidly teaching new skills, for generalizing across tasks by just feeding it video data, maybe from existing factory cameras, it's enormous.
But that kind of learning, processing all that visual data, it must require just immense computational power. Which brings us to Dojo.
Yes, Dojo. We usually hear about it for FSD, for training the cars.
Right.
But it's crucial to connect the dots. The robotics team is leveraging that same Dojo infrastructure. That massive compute power built for self-driving is now being used to train Optimus. That's a key Tesla advantage, that integrated compute backbone.
How does that translate, though? Training data for cars is about spotting pedestrians, lane lines. How does that help teach a robot to, say, pick up a tool or stack boxes?
The underlying process is similar. It's imitation learning, but at a massive scale. FSD learns complex driving maneuvers by observing human drivers.
Okay.
The Optimus team is applying that same concept. They feed the system video, presumably hours and hours of humans doing factory tasks, and the AI learns to map the visual input, like human grasps object X this way, to the robot's own motor controls. The type of data is different, but the AI training pipeline, the compute engine, is shared.
It really does sound like science fiction becoming factory reality. But okay, let's hit the brakes a bit. We need to ground this in the industrial world. Let's talk production versus promise, the gap between the slick demos and the factory floor.
This is the absolutely necessary reality check. Elon Musk has floated some incredibly ambitious production numbers, aiming for thousands of units by 2025, for instance.
Yeah, I remember that.
But independent reporting, like analysis from AI, shows a pretty clear pattern of missed targets so far.
The scaling has been slower, much slower than promised. Reports suggest maybe only hundreds of units actually built, not thousands.
And it might be more than just slow scaling. Some reports suggested production was actually paused, halted for significant redesigns.
That's a key detail.
It really is, because it points towards fundamental hardware challenges, not just software bugs or tweaking the production line. It's about the physical robot itself.
So we have these really impressive, almost startling tech advances happening in the lab, the Kunku balance, the AI learning, but a major bottleneck when it comes to actually building reliable machines at scale.
That's the critical distinction you have to keep in mind. Getting a robot to balance in a controlled demo, that proves the AI concepts are working, which is huge. But building thousands of units that are reliable, safe, cost-effective, and can work day in, day out in a tough industrial setting, that's a whole different class of engineering problem.
Right.
You can't just software update your way past the laws of physics like battery density or how materials handle stress and heat.
Speaking of physics,
Yeah.
let's drill down into those persistent technical constraints, the things that even the smartest AI can't just wish away. What are the big, maybe boring, but essential hardware hurdles for Optimus?
Well, I'd say the big three are endurance, heat, and strength. First, battery life, energy density. If you want this robot working a full 8-hour shift, maybe longer, the battery required is going to be heavy. And heavy batteries cut into the payload the robot can actually carry and manipulate. It's a difficult trade-off.
And heat. If it's doing real work, repetitive lifting.
Exactly. Continuous heavy work generates a lot of heat. Motors, actuators, joints, they all get hot. Thermal management is a classic robotics challenge. A robot that looks great balancing for a 30-second demo might overheat and shut down after 2 hours of constantly lifting 50-pound boxes.
It's like running a demanding game on your phone all day.
Pretty much. It gets hot, battery drains fast. That's the utility gap. And the third thing is just raw strength and durability, actuator power, joint torque. The robot needs to be strong enough for useful tasks, but also precise, and the joints need to withstand repetitive stress for potentially years. Can Optimus carry that, say, 50-pound toolbox upstairs repeatedly during a full shift without something breaking down? That's the multi-million-dollar question, isn't it?
Which leads directly into safety. If these robots are meant to work alongside humans, maybe eventually unsupervised, what needs to happen for a responsible rollout?
Oh, it demands absolute rigor. Total transparency in testing protocols, ideally verified by independent third parties. Not just Tesla saying it's safe.
Right.
Robust safety interlocks are non-negotiable. Things that guarantee an immediate safe stop if a human gets too close or if something goes wrong. And critically, clear rules governance about where and how these robots can operate, especially in complex, unpredictable environments, wet floors, obstacles, people moving around.
It's a huge challenge. And Tesla isn't alone here. We should probably pull back and look at the competitive landscape. It's getting crowded, isn't it?
Incredibly crowded, yeah. And well-funded. You've got startups like Figure making big waves, Aptronic, Agility Robotics, who have been focused on bipedal walking for a while. Plus, the big established industrial automation companies are definitely watching, and some are developing their own capabilities.
So with all that competition, what are Tesla's specific advantages? What makes Optimus potentially different?
I think it comes back to two main things.
Yeah.
That vertical integration in the data. They design the hardware, the software, the AI, all in-house. That can allow for faster iteration. And they have that massive FSD data set and the Dojo compute infrastructure already built. That's potentially a huge leg up for training the AI.
Still, competition isn't always bad. It can push everyone.
Absolutely. Competition drives innovation across the board. It pushes companies to create better components, actuators, sensors that might become available off the shelf. It forces improvements in control algorithms.
Yeah.
A rising tide lifts all robotic boats, so to speak. It benefits the whole field.
And as these robots get better and the demos get more convincing, more viral, it really shapes public perception. Which brings us to the ethical and social side of things. This isn't just tech anymore.
No, it's becoming a societal conversation, fast. The more capable these robots seem, the more urgent the need for discussions about governance and impact becomes. We're talking about major issues. Safety around autonomous machines, potential for large-scale job displacement, especially in logistics and manufacturing.
Privacy concerns too, right? Mobile robots with cameras everywhere.
Definitely privacy concerns. And questions about misuse. So lawmakers, ethicists, the public, they're starting to demand answers about testing, oversight, regulation. And that pressure is only going to increase as the robots look more human-like and capable.
The visual realism itself accelerates the need for that conversation. We need clear safety standards and regulations before these things are widespread, not after something goes wrong.
Agreed. Transparency about how they're tested, how safety is certified, that's crucial for building public trust, especially before they move out of controlled factory settings and into more shared spaces.
So let's bring it back to the listener. If you're watching this Optimus development, trying to figure out what's real progress versus just, a good PR video, what should you actually be looking for?
Okay, I'd say look for 3 key things as proof of real industrial readiness. First, actual multi-hour durability tests, not short, edited clips. Show it working hard continuously for a full shift. Duration is key.
Okay, number 1, endurance.
Second, independent third-party safety reports and certifications. Verifiable proof, not just internal claims about safety protocols.
Number 2, verified safety.
And third, demonstrated success in messy, unstructured environments. Show it navigating stairs reliably, working on uneven surfaces, maybe even outdoors in rain or dust. Real-world factory or warehouse conditions, doing continuous load-bearing work.
Number 3, real-world messiness. Got it. So summarizing then, Optimus is definitely showing big strides in control, coordination, partly thanks to that AI work with vision-only learning and Dojo.
Yes, the software and AI side seems to be advancing rapidly. The showmanship is improving.
But the long-term success, the actual impact of Optimus, really hangs on solving those harder, maybe less glamorous hardware and scaling problems.
Exactly. Durability, thermal management, battery life, and just being able to manufacture these things reliably, safely, and affordably at massive scale. That's the real mountain to climb.
We saw in the demo, the tech is getting much better at falling down and getting back up.
Right.
But the true test is, can it stay up, do useful work for 8 hours straight, day after day, and be provably safe while doing it?
And that leaves us and you, the listener, with a final thought to mull over, perhaps. Beyond just the technical specs and the demos, what does feeling ready for widespread, capable humanoid robots actually mean for us as a society? And how fast should regulation realistically move to keep pace?
Something to think about. We'll definitely keep tracking Optimus and the whole field. Until next time on The Deep Dive, stay curious.